We're going to take a look at questions 6, 7, and 8 from our homework last night, worksheet number 6. Scroll down to question number 6. Says, calculate the initial acceleration of an alpha particle. We've never used an alpha particle. We've never seen an alpha particle before, right? Listen, if you see something like this, you don't know what it is, you don't know what the mass is, what the charge is, look on your data sheet. All that information you need is on your data sheet. I gave you the charge in this question, but it's on your data sheet if you need it. Calculate the acceleration of this alpha particle if it is this far away from the electron and the alpha particle is free to move. We want to know the acceleration of the electron if it is free to move. So what do we have going on in this question? Hey, we've talked about that pretty much since day 1 of Physics 30, that we're not just looking at givens. We want to look at what's going on. What do we really know about this question before we take a look at givens? Well, we know that we're looking for an acceleration of a particle. And we know that in Physics 30, acceleration is always going to be found by F over m. So we need to get a force. What kind of force are we dealing with here? It's an electric force. So let's get the electric force in the way that we've got the electric force for the last couple of days using Coulomb's law. And then let's divide that electric force by the mass, first of the alpha particle and then of the electron. Here's the force that acts between the alpha particle and the electron. Coulomb's constant is 8.99 times 10 to the 9. And the charge, 3.2 times 10 to the minus 19 and 1.6 times 10 to the minus 19. The electron is negative, but remember what we do with a negative charge when we plug it into an equation? Always drop the sign of the charge. Always. No exceptions to that. Drop the sign of the charge when it's going into an equation. R is 2.0 times 10 to the minus 25 meters. And we got to square that. Let's pull up the calculator for this one to make sure that we can all get this. 8.99 times 10 to the 9 times 3.2 times 10 to the minus 19 times 1.6 times 10 to the minus 19. We're going to divide that by, use some brackets here, 2 times 10 to the minus 25. And we're going to square that. And it's going to give me 1.15072. Times 10 to the 22 newtons. So we got a big force there, right? We got a big force. But these things are close together. And of course, we know that the closer they get together, the bigger the force is going to be. It goes up exponentially as the distance gets smaller. Now, we want to find the acceleration of the alpha particle. The symbol, by the way, for the alpha particle is the Greek letter alpha. Call it QA, or sorry, AA if you want. Doesn't really matter. It's equal to the force divided by the mass of the alpha particle. And the force on the alpha particle is 1.15072 times 10 to the 22. How did I know that that's the force on the alpha particle versus the force on the electron? How did I know which particle, the electron or the alpha particle, to assign that force to? It's the same force on both of them. There was nothing like I have to decide which particle it goes with. It goes with both of them. If object A applies a force on object B, Newton's third law says object B will always apply an equal and opposite force on object A. So the forces have got to be the same. Now the only difference between these two questions is using the mass of the alpha particle, which is 6.65 times 10 to the minus 27, versus using the mass of the electron, which is 9.11 times 10 to the minus 31. Before we calculate these numbers, you guys can calculate those numbers, right? But before you look at those numbers, which acceleration do you think is going to be bigger? The acceleration of the alpha particle or the acceleration of the electron? Which is going to be a higher value? And why? Go ahead. Good. If you apply the same force on a train that's sitting on a track as you do on a little boy in a wagon that's on the sidewalk beside the track, then the little boy in the wagon is going to accelerate at a much higher rate, right? Because he's lighter. Him and the wagon are lighter than the train is. The heavier the mass, the smaller the acceleration. It goes back to something we were talking about in Physics 20 just this morning, Newton's first law, inertia, the law of inertia. Remember what inertia is? Tendency of an object to keep doing what it's doing, to resist a change in motion. The heavier something is, the more inertia it has. The heavier something is, the more it resists a change in motion. So if you got a big mass right here for an alpha particle versus a small mass for an electron, the alpha particle has more inertia, therefore its acceleration will be less. The electron has less inertia, its acceleration will be more. Is that okay? So we'll go number 7 then. Charge of 2 coulombs is touched with a second charge of 6 coulombs, then with a neutral object. We'll assume that after every time they touch objects, that they're separated, so we don't have at any point 3 of them touching each other at the same time. The first charge is then separated by a distance of 5.0 times 10 to the minus 2. What's the force that acts between the first and second charge? We got a couple things going on here, right? We want to find an electric force, and we find an electric force by using Coulomb's law. But objects are touching each other. And what happens when charges touch each other? What happens when objects touch each other? Yep. Yeah, they try to balance. And we're going to assume that they do balance. We're going to assume that the size and shape is similar enough that they will balance. If we're going to do that, then we better draw that little table that we've drawn in problems like that before. We start off with 2 coulombs, 6 coulombs, and 0 coulombs. First touches the second. 2 and 6 is 8. Divided by 2 is 4. So it becomes 4, 4, and 0. Then the first one is touched with a neutral object. 4 and 0 make 4. Divided by 2 is 2 and 2. So my 2 charges that I care about here are 2 coulombs and 4 coulombs. So we're going to say F is equal to K, Q1, Q2 over R squared. Q1 is 2, Q2 is 4, and R is 5 times 10 to the negative 2. We're going to square that. Prediction here, Matt. Going to be a big force or a small force? I think it's going to be a pretty big force too. We're dealing with a big constant like we always are, but this time we're dealing with some pretty big charges, right? 10 to the 0 big charges. The distance, it's a lot bigger than it was when we had the electron and the proton, right? But it's still a pretty small distance here. I think we're going to get a pretty big force as well. What is the value of that force? That's not, no, anybody else? Yeah. 2.88 times 10 to the 13. So it's not nearly as big of a force as we've seen with some of the other questions, but it's still a pretty big force. Okay? We want to find the acceleration. We divide by mass. We don't have any masses here, but if we had one, we could do that. 8. Object 1 has an initial charge of 1 times 10 to the negative 5. 2 is negative 2 times 10 to the minus 5. I'm going to circle that because I'll forget that that's negative. When you're my age, you forget everything. Okay, it's so easy to forget a negative there. You know what? Even when you're your age, it's easy to forget a negative there. Object 3 has a charge of negative 3.5 times 10 to the minus 5. We're not going to pay any attention to those when we're calculating the force, KQ1, Q2 over R squared, but we got to pay attention to those when we're determining what the charges are after they touch, right? 1 touches 2, 2 touches 3, then 1 is brought away from number 3. We want to find the force that acts between charge 1 and 3. Let's draw our table again. We have 1 times 10 to the minus 5. We have negative 2 times 10 to the minus 5 and negative 3.5. 1 touches 2. 1 and negative 2 becomes a total charge of negative 1. Divide that by 2, it becomes 0.5, negative 0.5 times 10 to the minus 5. Then 2 touches 3. Negative 0.5 and negative 3.5 becomes negative 4. Divide that by 2 and it becomes, so negative 2, and negative 0.5. We want to find the force between 1 and 3. Q1 becomes 0.5 times 10 to the minus 5. Is it okay to say 0.5 times 10 to the minus 5? That's the same thing as saying 5 times 10 to the minus 6, right? But why would we risk moving the decimal place over the wrong way or messing up with that some way? Like, look, we kept dividing by, adding and dividing by 2. We ended up with 0.5. Stick with it. 0.5 times 10 to the minus 5. It's not scientific notation, but who cares? Really, it's not a final answer. I dropped the sign of the charge, right? Not the exponent, but the sign of the charge. R is 2 times 10 to the minus 3. And we got to square that. What do we get for that one? 2.2475 times 10 to the 5 newtons. Agree with that? Which is what, 2.25? If we're asked to express that on a diploma exam or on a unit test or even on a quiz, there's a couple ways that we could be asked to express that. Sometimes it's, a lot of times it's A decimal BC times 10 to the D. What are the values of A, B, C, D? The answer would be 2255. Sometimes it says B times 10 to the W. There we want the value of B, which would be 2 decimal 25. So same answer expressed 2 different ways depending upon how they ask. Okay, on a quiz, that's where we really want to nail this stuff as quizzes, right? If you're ever not sure how to fill it in on a quiz, like ask me, and I'll fill it in for you on a quiz, as long as you have the answer. We don't want to lose 2% on our diploma exam because we fill it in wrong, right? Good there? All right, well, let's move on a little bit. Here's a question that you haven't seen before, although your homework questions were much like this. I'm going to get you to spend about 60 seconds at your desk to see if you can do number 42 by yourselves, please. 2 conducting spheres have identical surface areas. What are they really telling us? Say they have identical surface areas. We've seen this context before, right? And I've asked this question before. What are they telling us there? They're going to balance out. Now, even if they don't tell us that they have identical surface areas, we're going to assume that they balance out. They're just being complete here and being thorough, telling us that they will balance out. Sphere A is 4.5 microcoulombs. Sphere B is negative 2.4 microcoulombs. And they're separated 2.5 centimeters here. So A touches B, 4.5 plus negative, is that 2.4? Yeah, negative 2.4 divided by 2 gives me, I think it was 1.05 microcoulombs. The force that acts between them is AQ1, Q2 over R squared. Uh, 1.05 times 10 to the minus 6. People say, like, how do we convert this to coulombs? Check your data sheet. You're going to see a micro is 10 to the minus 6. So all you're literally going to do is replace the little Greek letter mu with the exponent 10 to the minus 6. So 1.05 microcoulombs becomes 1.05 times 10 to the minus 6 coulombs. I'm going to just square that because it's 1.05 times 1.05, right? And we divide that by R squared, 0.025 squared. What do we get when we do that math? 15.9? Right? All right, I think we're okay with this. Okay, I think we've more or less mastered this type of question. What happens, though? What happens To go a little bit further with this, when we have 3 charges, not just 2 charges, everything up to this point has involved the electrostatic force between 2 charges. Sometimes there's been 3 charges. Charge 1 touches charge 2 touches charge 3. What's the force between 1 and 3? But we've never tried to find the force acting as a result of 3 charges. That's what we're going to learn how to do today. Let's see, we've got charge 1, charge 2, and we've got charge 3. Charge 1 and 2 are 5 centimeters apart. Charge 2 and 3 are 4 centimeters apart. Let's say this is minus 5 microcoulombs. This is plus 2 microcoulombs. And this is, let's make it minus 3 microcoulombs. We want to find the force on charge 2 as a result of charge 1 and charge 3. Both of these guys are applying forces on charge 2. We want to know what the total force is, the net force between those 2 charges acting on charge 2. So what do we got to do? Let's go back to physics 20. If we have more than one force acting on an object, we always do the same thing. I don't care whether it's in the context of one of those inclined planes or vertical circular motion, or whether it's in the context of 3 charges in a row. When we have more than one force acting on an object, we always draw a free body diagram. Always. We got 2 forces acting on charge 2 here. We got 2 forces acting on all of them. But if I want to find the net force on charge 2, then I have to pay attention to the forces acting on charge 2. Look at charge 1 and charge 2 first of all. Charge 1 is negative, charge 2 is positive. Do they attract or repel? Yep. They're going to attract because they're opposites, and opposites attract. All right. If they attract, have a look at my fists up here, okay? Left fist, charge 1, right fist, charge 2. If they attract each other, look what happens to them. Charge 1 goes to the right, charge 2 goes to the left. I'm going to draw the force on charge 2 because I'm trying to find the force on charge 2. Charge 1 also goes to the right, but I don't really care about that because that's not what I'm trying to find. It's like last year when you were solving vertical circular motion problems and you were analyzing the roller coaster cart at the top, right? The net, the normal force downward, the force of gravity downward, right? Remember that? We looked at the forces acting on the roller coaster cart. Now, if the Earth pulls down on the cart with a force of Fg, then the cart pulls up on the Earth with the same force. Just don't notice it because the Earth is so heavy. We never paid any attention to the force acting up on the Earth, right? Because we were trying to analyze the roller coaster cart. If we're trying to analyze object number 2 here, sure, object number 1 is pulled to the right as a result of that, but we don't care because we're trying to analyze a different object. If the time comes when we have to analyze object number 1, then we care about which way it's pulled or pushed. Force on number 2 is to the left because it's attracted towards number 1. Okay, what about 2 and 3? Positive and negative opposites, once again, attract. Let's look at my fists. Charge number 2 and 3 come towards each other. 3 goes to the left, but who cares? 2 goes to the right. The force of 3 on 2 is to the right. So there's my free body diagram for object number 2. If you ever have to find the force on number 3, then draw a free body diagram for number 3. But until that time, don't waste your time. You guys remember what you always did in physics 20 at this point when you drew your free body diagram and had all of the forces? Remember that next step? Whether it was that inclined plane question or that elevator question or that vertical circular motion question, we always said F net equals the sum of the forces. That's exactly what we're going to do here. F net is the sum of the forces. The net force on number 2 is equal to F12 plus F32. Now, we got to find both of these forces, right? That's easy enough, though. F12 is KQ1, Q2 over R squared. F32 is going to be K times Q3 Q2 over R squared. So 8.99 times 10 to the 9 times 2 times 10 to the minus 6 times 3 times 10 to the minus 6. Say this side of the room, Ben's side of the room, grab the force of 1 on 2. And let's say Haley's side of the room, find the force of 3 on 2. This one's 35.96 newtons. And this one's F32 is, here we got that? .33 Haley, 0.71 newtons. All right, let's plug those numbers in here. Am I missing anything? Yeah. Yes, the 35 is negative because it's drawn to the left. You might be starting to see now why it's so important to me that you leave out the sign of the charge in equations. Okay, if I plug in the sign of the charge into both of these equations, I'm going to end up with a negative 35 and a negative 33. Now, I can recognize that that just means that they're both attractive forces, but what will happen a lot if we get a negative 35 and negative 33, what will happen to us a lot is that we'll just automatically, at some level, think they're both to the left. We'll add them up both as negative values. Okay, we're mixing and matching sign conventions there. We drop the sign convention for the type of charge when we plug it into an equation. We always get a positive value for force, and then we figure out the direction, positive or negative direction, some other way, right? Our free body diagram, attractive or repulsive, right? We add these up, and we're going to get what? Negative 1.2-ish? No, 2.2? Negative 2.25 newtons, which, because the only sign convention we're using here is left-right, that means 2.25 to the left. All right, I'd like you to take a look at page 533, please. Question number 1 right now, and then if you have time during class today, take a look at question number 2 as well. If you don't, then take a look at question number 2 for homework. This is a challenging question. I'm going to put a star by it because it's a real challenge question, but give it a shot. Okay, you got some time tonight, give it a little bit of a shot. And if you can get it, means you're in really, really good shape for this. Okay? It's probably a little bit harder than what we'd see on a quiz or on a test. But give it a whirl. All right, let's have a look at number 1 now that people have had a chance to work on it. Because a metal sphere with a charge of negative 2.5 is 1.5 centimeters. Right away, before I go any further, to the left of a second metal sphere with that charge, there's a third one that's this far to the right of the second one. What's the net electrostatic force on the second one, the middle one? So we'll call this number 1, and it's negative 2.5 times 10 to the minus 9 coulombs. Number 2 is 1.5, positive 1.5 times 10 to the minus 9 coulombs. And number 3 is negative 1 times 10 to the minus 9 coulombs. And our distances, 0.015 meters and 0.02 meters, right? 2 divided by 100. Find the net force on number 2. 1 and 2, which do they attract or repel each other? 1 and 2. Good, they attract each other. Now, which way is number 2 going to move as a result of that attraction towards number 1? Good. So we're going to say F12 is to the left. We don't really care what happens to number 1, right? 3, 2, 3 and 2, opposite charges, they're going to attract each other as well. So 2 is going to go which way as a result of that attraction? Why? Which way is number 2 going to go? Left or right? Good. So it's going to move to the right. So we're going to say F32 is to the right. We'll calculate both of those forces. 8.99 times 10 to the 9 times 2.5 times 1.5 divided by r squared. What do you end up getting for F12 there? Kaylin, I know you get the right answer for this. So what's the value of F12? 10 to the negative 8. Thank you. F32. Dom, you got that one? Go ahead. 10 to the negative 4. Okay, so Kaylin, you must have got the wrong exponent there. Okay, so if you left it in centimeters, you get 10 to the negative 8. If you convert it to meters, you get 10 to the minus 4. Okay, thank you. Don't forget to convert that, right? That's why we circle that centimeters, right? Just to draw attention to it so we don't forget to convert it. Dom, do you have the value of F32? 10 to the negative 5 newtons. Agree with that? Yep. All right, so now we got to add them up. We're going to say F net is equal to the sum of the forces. It's going to be F12 plus F32. And we're just going to make sure we plug them in with the right signs. 1.49, it's to the left, so we're going to make it negative. And F32 is to the right, so we're going to make it positive. And we do that, we should get 1.16. But it's negative. One more example with you here. 10.5 on 534. It says a small metal sphere with a negative charge is to the left of another one with a positive charge. Then there's another one that's below sphere B. So we've got, what do we got here? We've got A, B, and then we've got sphere C that's below it. A is negative 2.1 times 10 to the negative 6. B is 1.5 times 10 to the minus 6. And C is 1.8 times 10 to the minus 6. What about our distances here? 0.02 meters. And this one's going to be 0.03 meters. Uh-oh. Or is it uh-oh? How many people feel right now like maybe they could get this question correct, even though we haven't done anything like this before? Yeah, we know what to do with this, don't we? We know what to do with this. Just take a step back from it and think about it, right? We know how to find electric forces, and we're going to have to find electric forces. We know it's in 2 dimensions, so we're going to have to deal with it vectorially. We know how to do that. We've done that lots of times in Physics 20 and some in Physics 30 back in the last unit. We know exactly how to do this question. First of all, draw a free body diagram. B is pulled towards A because it's an attractive force. We'll call that FAB. C pushes B away because they're both positive. It's a repulsive force. So B is pushed away from C. Right there. All right. We get the value of both forces. FAB is KQA QB over R squared. FCB is KQC QB over R squared. And then what do? We got to add these vectors together. We say FAB, whatever its value is, plus FCB, whatever its value is, equals the net force. And we know how to find that. We do the Pythagorean theorem, right? And theta is equal to the inverse tan function. We've done this a million times between last year and this year. I haven't actually gone through the math in this question because I really feel like it's the same thing as we've done. Right? It's just putting a couple of different things together. It's putting our vector analysis together with our Coulomb's law stuff. Notice what I'm doing here? I'm still, in a sense, saying F net is the sum of the forces. I'm still adding forces together, right? But when I added forces together in the last problem, it was one dimension. When I'm adding forces together in 2 dimensions, I got to draw that vector diagram. I have to. I can't just say, you know, whatever this is plus whatever this is. I got to say whatever this is vectorially plus whatever this is. Draw that vector diagram and solve. I'd like you to work on now 2 questions that go along with that, which is on page 534. So you got a good 19 minutes to work on these 2 questions and this second question on page 533 if you haven't finished it already.